statistical data hub platform, which is based on the statistical register. The platform will allow data to be linked and combined with various institutions to create new value. Also, latest personal information protection technology studied in the academia, such as homomorphic encryption, will be discussed to find new breakthroughs to harmonize data protection and utilization. We hope that innovative cases linking data from various sources, such as satellite data, can serve as an opportunity to increase the timeliness, granularity of statistical data and expand the scope of its use. Lastly, I would like to thank all of those who have worked to host this session, and I would like to once again extend my heartfelt gratitude to the presenters, to the panelists, and participants who are joining both on and offline. Thank you very much.
Thank you, Commissioner Han. Before we begin, let me walk you through this session. Under the topic Innovating the Use of Statistical Data and the Current and Future Use of Statistical Data Through Innovation, we will have presentations from Professor Keun Kwan-Yu from SNU, Professor Vainod Vaikuntanathan of MIT, and Director Paul Schreier of the OECD Statistics and Data Directorate. Next, Professor Liu will moderate a panel discussion where Professor Chun Jung-hee of SNU will join the three presenters. Without further ado, we will start the presentations. First, Professor Keun Kwan-Yu is the professor of economics at SNU and former commissioner of Statistics Korea, whose research area covers diverse areas through statistics. The topic is Hub and Spoke model for governmental data, data linkage, and data security. Professor Liu will show us how government statistics governance can be innovated through a hub and spokes model to reconcile the protection of personal information and the use of statistical data, demonstrating the role of government in real case applications. Please welcome Professor Liu to the stage.
Thank you for coming to this wonderful session. I very much appreciate Mr. Jang Dae-hwan for allowing this session for Statistics Korea. And also I appreciate Paul Schreier and Vainod Vaikuntanathan for coming all the way to Seoul for this very important event. So let me start. So today I will talk about hub and spoke model for governmental data. Why do I want to say this? It's simply because the data is pretty much distributed among different governmental ministries and organizations in Korea. And basically, the Korean citizens are required to answer survey questions from the governmental ministries. Then the ministry has an obligation to protect Korean people's privacy. Therefore, even a single ministry is not allowed to share the data with other ministry if there is no guarantee for data privacy. That's why we need a scheme to perfectly protect individual privacy while trying to utilize useful information by sharing and linking different data sources across different governmental ministries, organizations. That's the starting point of why we are thinking about the concept of a hub and spoke model, so-called. Nowadays, as you know, some people prefer to use the term AI and the big data, but I simply would like to say that it's a marriage of three bigs, easier to conceptualize. Data is getting bigger. Accordingly, model size is getting bigger, whether you call it AI model or machine learning or whatever. So in my view, it's simply bigger model. And then the marriage of big data and the big model are supported by big computing. Nowadays, parallel computing, CPU, GPUs, a lot of improvements support the marriage of big data and the big model. And in certain areas, the marriage of three bigs generate something big. That's the world we are living with. Privacy protection issues. Some people, including governmental agencies, including lay people, media, they somehow believe that so-called anonymization or pseudonymization will solve the privacy issue. But personally, I don't think so. Why? If you remember childhood memories, you may have a good memory of 20 questions. So one person has certain object in mind and then give hints. Single hint cannot reveal the identity of the object in mind, but by asking multiple questions, you are coming close to the identity. So in the end, after asking 20 questions, you get to know what the content is. That's the nature of 20 questions game, which means that if one department or ministry or organization release one piece of information, then that doesn't compromise individual privacy. But if different informations are combined, then in the end, your identity is revealed. So anonymization or pseudonymization is not the ultimate answer, in my view. That's exactly the same problem like cost of dimensionality. If you are from statistics orientation, you know what cost of dimensionality means. If you have multiple features, then the number of observations satisfying jointly all those features are very tiny. In the end, either empty cell or just one or two people, which means that you cannot estimate whatever statistical concept based on that few observations. That's the cost of dimensionality in non-parametric statistics. But in terms of identification, there's cost of identification. Because after revealing many features, the person or organization satisfying all those conditions are either one person or two person, which means that your identity is released. So there is a trade-off between linking and protecting personal information. So so far you have only one or two undesirable solutions: stronger linkage and weaker protection, or weaker linkage and stronger protection. Right now, Korean government is adopting, in a sense, second package: weaker linkage and lesser use of data. Therefore, government can protect individual privacy. That's the world in which we are living with. So there comes the need to design new paradigm, which we call statistical data platform. This is a spokes and hub and spokes model for governmental data. Hub and spokes concept originates from airline industry. So if you visit some local area, then you go to hub airport first, and then from the hub, you go to local airport. That's basically hub and spoke concept. In the case of governmental data, the hub is basically, well, as an organization, it can be Statistics Korea, or as a concept, it can be statistical registers. So for individuals, we have a list of 52 million Korean people. If it's establishments, we have a list of about 6 to 7 million active establishments in Korea. And then using that list, conceptually, we can link all spokes across different government organizations, institutions, or ministries. So that's why we think about this hub and spokes model. So people are using the term water dam. So similarly, they are talking about data dam. So all of a sudden, people think about water dam as a configuration. Then you don't know where the water is coming from and which water is mixed with which other water. If statistical data are managed like water dam, that's a total chaos. So we want each data source is perfectly protected and then linked and analyzed in a safe way. That's the diagram depicted on the right-hand side. If you are familiar with the spreadsheet, right now in Korea, different futures of individuals and establishments are kept under different organizations. So you see the vertical bar, which is blocking marriage of different data sources, linkage of different data sources. But in the future, by using new developments, we want to safely link data across different departments, and we want to safely analyze the data out of many richer information. So this is a concept, diagrammatic expression of a hub and spoke concept. In the hub, there exists statistical registers, whether it's individual and household registers or business registers or whatever. And then by using this list, you can link every other different data sources scattered across different departments. Regarding privacy protection, we are going to use homomorphic encryption. In this conference, two world-best scientists are here. Professor Vaikunthanadan, he is leading homomorphic encryption in the academic world. He is here today. I'm very happy with that. And from Seoul National University, Professor Chun Jung-hee, he is the one developed CKKS scheme with his students. Again, I'm very happy to see him here on this spot. So we are going to heavily utilize the development homomorphic encryption for this purpose. And then on top of that, we are using differential privacy as a complement, also synthetic data. I'll explain about these concepts a little more over time. Homomorphic encryption. Encryption and computation are commutative. Commutative means that you can switch the role, switch the order, which means that in a typical computation, you first encrypt the data, and then whenever you want to compute something, you decrypt the data. In that process, encryption and decryption, in that process, privacy can be breached. But because of this commutative property of homomorphic encryption, you encrypt the data. And then you don't have to decrypt the data for computation. You compute on the encryption state. And then finally, when you need some results in plain text form, only at that point, you decrypt the data. So it's much more secure scheme. So in that case, we have to devise a key management scheme. And this scheme is based on my personal communication with Professor Chun Jung-hee and his team, including Dr. Hong Jung-dae. So there is a trusted third party, and two agencies are generating secret key. Secret key is personal private key, SKA and SKB, and then the third party combines two secret pieces and then generates public key based on two secret keys. And then only public key is known to anybody, while secret keys are kept only by individual agencies. And then each party encrypt the data using the public key. Because both parties are using the same public key, the two data can be merged in encryption format. And then finally, they share the results, and the results can be decrypted only on the mutual agreement. So you don't like complications, so I conceptualize this clock. The clock is at 12 o'clock initially. That's unlocked. When it turned 180 degree clockwise or counterclockwise, at 6 o'clock position is decrypted, locked. But agency A, secret key A, graphically correspond to two pieces of operating power, turning the clock from north to east or from west to south, as depicted by a red arrow on the left circle. Agency B, on the other hand, has power to turn the clock from north to west or from east to south. So, as you can easily figure out, no single agency can turn the clock from 12 o'clock to 6 o'clock, which means that those signals can decrypt the data. Only when they coordinate, they can do that. That's the scheme. And one morning, I thought about this clock, and I thought that this is an easy way of communicating with lay people. So that's why I use this one. Differential privacy. Basic idea is that you add noise to the original signal. So you can only observe the data in noise-contaminated form. And then there are two versions, global differential privacy and local differential privacy. But for the lack of time, I will just skip this part. Synthetic data. Once data are encrypted, then the data is changed from plain text form into encrypted form. Encryption, obviously, is inconvenient. The data is heavy. It takes a bigger storage space. So dealing with encrypted data is not that much pleasant or easy. So we want to generate kind of simulated synthetic data for exploratory purpose, for practice purpose. Then through that synthetic data, which doesn't contain individually sensitive information, but which contains overall similar structure with the original data. So by using synthetic data, you build a model, you do some exploratory statistical analysis, and then after enough practices, once and for all, you apply the developed model to the original encrypted data. That's the scheme I have in mind, we have in mind. So let me talk, by the way, how much time do I have left? How much time do I have left? 10 minutes or less than 10? 10 minutes? 5 minutes? 10 minutes, okay, thank you. So regarding applications, first, healthcare information. Many pieces of healthcare information is very sensitive. Therefore, privacy protection is very important. In Korea, I think we have world-class health-related data, but the linkage is problematic. So by using homomorphic encryption, I think we can utilize health-related data more actively in the future, as I hope. Household death statistics. As Commissioner Hanun mentioned, Statistics Korea is currently compiling household death data. So far, it's a sensitive information. Therefore, even though it's a very important issue in Korea, because household death is increasing, there hasn't been any complete picture for household debt at the entire household level. So it's a wonderful thing that Statistics Korea is conducting that important job under the leadership of Commissioner Hanun right now. It's a very exciting time, I think. Again, privacy protection is very important. Pension statistics. Again, as Commissioner Han mentioned, old age poverty problem is an issue in Korea. But national pension, retirement pension, individual pension, reverse mortgage pension, farmland pension, they are all operated separately. But what you are interested in as a person or as a couple, how much you can be covered by all different sources of pension income. But that has not been compiled yet in Korea. So fortunately, different government organizations have come to an agreement to share information, to compile comprehensive pension statistics, which is a good thing. Just let me give you simple statistics. Fortunately, we have Mr. Chief OECD statistician Paul Schreier here. According to OECD statistics, Korea is #1 in terms of old age poverty. About 4 people out of 10 are recorded as living under the so-called relative poverty line. So which rate is about 3 times higher than OECD average. Can you believe that 4 out of 10 old Korean people are under poverty? Do you think this is true? Personally, I don't think so. I personally think that this number is all exaggerated. Why? Relative to typical OECD old age people, Korean old age people have more of their asset in real estate. But as you know, real estate doesn't generate dividends or interest payments. Therefore, when you only compare income flow, Korean old age's poverty is underestimated. As a result, poverty level is exaggerated. So to have a hint about that, I get some information from household survey for finance and the welfare in Korea. But for the lack of time, I'll skip the details. As you see, old age people have a lot of assets in terms of real estate, which is much higher than OECD average. So if you only address that aspect, I think Korean old age people's poverty level would be reduced. Then personally, I think that this will be the starting point to come up with a social agreement regarding pension reform. As of now, the marriage of two things prevent pension reform. One is old age people is terribly poor according to OECD statistics. That's number one. Second, because of population structure, old age people has a lot of voting power. Because of those two facts so-called, it's not easy to reform national pension. So we have to start from the basic statistics. If you look at this table, this is joint distribution of income and asset across segmented by age. If you are below 65, income and asset goes together. But if you are retired, aged over 65, then as you see, there are a lot of people who are asset rich, even though they are income poor, which signals that Korean old age people's poverty level has been exaggerated. I would rather say that. I will say that it's exaggerated. So 10 minutes remaining from now. Okay, thank you. So I don't have to speed up. So I'm more relaxed. Okay, let me explain this survival analysis of small businesses in Korea. This is a joint project with one of the local government. So we combine Statistics Korea's business registers with Gyeonggi Province small business information for years 2015 to 2020. And we computed descriptive statistics and so-called logistic regression as well, pretending that Statistics Korea doesn't believe Gyeonggi Province, and the Gyeonggi Province doesn't trust Statistics Korea. So two organizations are mutually enemies, but still they can cooperate using on the data protection. This was an exercise we conducted. I will skip the details, but basically the dependent variable is an indicator whether an establishment has survived certain period or not. And then as covariates, we include many characteristics which affect survival of firms. Well, I know that you don't like numbers, so I will skip this part. I'll give you interpretations rather. According to the results obtained by combining data from two different organizations, we get to know that establishments with a bigger sales amount face a lower death rate. As you expect, bigger one survives longer than smaller ones. And establishments with a bigger shop space face a lower death rate, which is again not surprising. And the shutdown rate, which is death rate, is higher in developed business areas, because in developed business areas, entry-exit is more prevalent than other areas, so which is not surprising either. Why surprising is that shutdown rate is lower during the COVID-19 period, which was a little bit surprising initially. During COVID-19 period, shops faced trouble, so I expected that the shutdown rate would have been higher during that particular period after controlling for other factors. But surprisingly, the result turned out to be opposite. But later I realized that it's consistent with what shop owners are crying. They are crying that there are no alternatives, so they cannot shut down, even though the business is not going well. Okay? So that's what we found. And regarding life cycle effect, we observed that shutdown rate is low for the first year after birth. So if you imagine that you set up a small coffee shop, then you wouldn't shut down the shop for the first year, so which is natural. But from the first year up to third year, the shutdown rate is higher. You cannot survive. And then after 3 years, it stabilizes. That's what we observed using the small business data on Gyeonggi province, and after linking that data with the Statistics Korea business register database. Okay, final section. We are currently at Statistics Korea conducting $15 million projects, which is a big chunk of money for Statistics Korea. It's comprised of 4 elements. Regarding privacy preserving, we are developing homomorphic encryption. And as a supplementary tool, we are also developing differential privacy. And to improve functionality, we are investing in developing compiler for specifically designed for homomorphic encryption. And then, as I mentioned, we are also investing in operationalizing the concept of synthetic data from Statistics Korea's perspective. I think that regarding homomorphic encryption, the next speaker is Professor Baikun Tanadan. I think he will deliver much better talk than I briefly review. So I'll skip this part. So according to the plan, by the end of year 2024, Statistics Korea will have an initial platform based on homomorphic encryption. So according to the platform, each agency can decrypt the data, and then at the server is equipped with homomorphic encryption tools, and then basically other organizations on the demand side of data can use information coming from the server. So that's the scheme Statistics Korea has in mind. Thankfully, Professor Chun Jung-hee is involved in this project with a lot of established researchers who developed so-called famous CKKS scheme. C stands for Chun Jung-hee, and KKS stands for each of his students at Seoul National University. We are very happy to have them involved in this project, I think. So this is a kind of roadmap. So develop the scheme by year 2024, And then by using this platform, hopefully Korea can contribute to the global world by introducing and implementing this concept, so-called hub and spokes model. Thank you very much for your listening.
Thank you very much. To reconcile privacy protection and statistical data use, government statistical governance can be innovated as shown. Thank you for the presentation. And the next speaker is a professor of MIT EECS and a world authority in homomorphic encryption, or HE, the latest cryptographic technology. Professor Vainod Vaikuntanathan will present homomorphic encryption and machine learning challenges and opportunities. The HE is the latest technology in information protection. Linking and using statistical data has had the trade-off of personal information, but HE offers a way out. Please welcome onto the stage Professor Vaikuntanathan with a warm hand.
It's really a pleasure to be here. Thank you to Professor Ryu, Professor Cheon, Commissioner Han for inviting me. You heard a really excellent talk from Professor Ryu just now. It's hard to follow that up with another talk, but let me try my best. Great. So what I would like to tell you is, again, following up on the last talk, a little bit more about homomorphic encryption, what it is, what can we do with it, and the challenges and opportunities that lie ahead. I would really be preaching to the choir here when I say that today we stand right in the midst of a revolution in data science. And really the gold rush of our age is to collect data, analyze it, derive insights from it, and use it to build products that make our lives better every day. In order to realize the full potential of data, it's not enough that data lives in silos owned by different entities that do not work together. The different stakeholders in the system, the different parties that hold various types of data, the model owners that own the algorithms that operate on this data, and the computation infrastructure providers that provide the tools to do the necessary learning here, they all have to come together and work together and collaborate to extract the full potential from this data. It is not hard to imagine the extent of knowledge that we would gain, we would derive by putting data together. In fact, every one of you here at the end of my talk can come up with your own examples of the kind of insights you can learn by putting different types of data together, what we can learn from the collective as opposed to the individual. For example, you heard several examples of this from the last talk already. As yet another example, I have a colleague at MIT, he says sort of half seriously, half jokingly, that if only we could put all the genomic and phenotypic and medical data and medical records in the world, we can cure cancer today. Only half jokingly, I suppose, but his point really is that the benefits of combining data and collaborating on data is so immense that it's only our imagination that limits us at this point. So here's an example of genome-wide association studies where you can put together genomic data and medical records and try to find the genetic markers for various diseases. In this example, you have different parties that one party that holds the genomic data and other parties that hold medical records and phenotypic information. Here's another example, and it really doesn't have to be data and data. You could have a party that actually has a model, as an algorithm really, we call that a model these days. This model takes an image, an MRI image, and tries to determine if it has a lesion or a tumor and so forth, really in the field of personalized, automated sort of prediction of diseases. And here again, you have two parties, one that has the model and one that has the data. It's the user that has the data and they want to run it through the model and get the prediction. And they both have privacy concerns. The user doesn't want to reveal the image to the model owner. In fact, we know at this point that medical images are incredibly revealing. And the model owner does not want to put the model out there for several reasons, for economic reasons, and just the fact that the model itself could reveal information about the data used to train it. So both parties have privacy concerns, and can you actually make this sort of prediction as a service possible while preserving privacy considerations? Here's a third example from a different vertical, banks and anti-money laundering. So money laundering networks can be very complex. They could span multiple accounts and multiple banks. And so almost by definition, robustly detecting money laundering networks requires the banks to put data together and learn from the collective, learn the networks from the collective. And like I said before, this is really, I can keep going on and on and on. In fact, I'd be, you guys should sort of think about your own examples, and I'm sure you can come up with many by the end of my talk. Private contact tracing, secure benchmarking. In fact, I'll talk about that a little bit later in my talk. And collaboration doesn't have to be within the same vertical. It doesn't have to be within healthcare and within finance. It could be cross-industry collaboration. For example, retail and finance can collaborate to learn sort of things about shopping patterns of individuals. Unfortunately, collaborating on data is far from easy. Privacy concerns, regulatory reasons, and just sort of the interest of sort of keeping your own business secrets and intellectual property often prevents parties from collaborating on their own, on the collective of the data. So it almost seems like privacy and these other considerations are standing in the way of scientific progress, societal progress, and just human progress in general. And the question we have to ask is, does this have to be the case? Can you devise methods to collaborate on data while preserving security? And really what I want to tell you about, again expanding on the last talk, is one of the technologies that we have come up with in cryptography to address this problem. So before we go there, let's sort of examine two strawman solutions. The first one, again, Professor Ryu mentioned already, is that of anonymization. Anonymization doesn't sort of do the job for several reasons. One, because there's really a cottage industry at this point of de-anonymizing sort of supposedly anonymized data sets. So really, anonymizing data is very hard. You can often get real information about individuals, particularly by putting one supposedly anonymized data set with another supposedly anonymized data sets. These linkage attacks are extremely devastating for anonymization schemes. So that's number one. Number two, some data can just not be anonymized. Genomic data, for example. How do you anonymize genomic data? Images, medical images are again extremely hard to anonymize. The third reason is that anonymization often is at odds with linking data. So often you want to sort of link two data sets on a common identifier, and if you remove this identifier, how do you link data sets? You can try using pseudonymous identifiers, but that actually goes back to the privacy question, and often you can actually de-anonymize pseudonymized data sets. The other thing you might think of if you are a cryptographer, or if you've heard this somewhere, is to encrypt data. And sort of encrypting data is like putting data in a box and locking it, right? So that's the ciphertext, that's the encrypted data. It's like a locked box with data inside it. If you think about it for a moment, that's a non-starter. That's a complete non-starter, because encrypting gives you privacy. That's what it's designed to do. But it also completely prevents you from using this data in any meaningful way. So it sort of seems like a 0-1. Either you open the box and you see the data, or the box is closed and you can't do anything with the data. Or at least that was the conventional wisdom for a very long time. And what happened about a decade ago is that we, as a community, as a community of cryptographers, we invented this notion of homomorphic encryption, which lets us make sense of, lets us bridge the two tasks, namely keeping data private and using it for useful purposes. So here is my version of my interpretation of homomorphic encryption. Let's think about the setting where one party, the hospital, has a model, the other party is a doctor that has an image, and she wants to get it classified using the model. Right? So this is what we saw a few minutes ago. So with encryption, the doctor, she generates a pair of keys, a public key, which you should think of as a lock, really, and a private key, which is really a key that you open the lock with. What she does is she encrypts the data. She encrypts the image, so puts the image in a box, locks it, and sends it over to the hospital. Now, what homomorphic encryption does is it's a very special kind of locked box. So you should really think of it as a locked box with a glove compartment attached to it. So, the hospital on the other end can put their hands inside the glove compartment and manipulate the data without actually seeing it. That's sort of, if it sounds magical and science fiction, that's what it sounded like to us cryptographers for decades, until we figured out that really you can actually do it. Right, so once this processing called homomorphic computation is done, the box actually has the result of the computation, which gets sent back to the user, and she has the key, she opens it and gets the result. Right? So that's how homomorphic encryption operates. So again, this notion was invented back in the 1970s at MIT by three scientists, Ron Rivest, Len Edelman, and Mike Dertouzos, and they had a dream. Their dream was that you should be able to design an encryption system which can allow arbitrary computations to be done while the data remains encrypted. That was the dream. For a long time, that dream sounded like a pipe dream, and the first sort of real breakthrough came in 2009 when Craig Gentry came up with the first candidate construction of fully homomorphic encryption, and that means that you can actually take this locked box and you can do any computations on the data inside. What happened, and this I remember very clearly more than a decade ago, is that there was an article in the Forbes magazine that said, look, this looks really, really amazing, but it'll never become practical. There's no chance. And for a good reason, because the initial demonstrations of homomorphic encryption required gigabytes to encrypt a single bit, if you can imagine that sort of thing, and hours and hours to do a single Boolean gate on the encrypted bits. So the skepticism is understandable, right? But that's the thing about technology, right? Once you have a little crack in the wall, that crack tends to become wider over time, and at some point you burst through it and you see the promised world. Just let's think about satellites, which we take for granted. What did Sputnik do? What did the very first satellite do? Does anybody remember? It sent beeps. It went around the Earth, it sent beeps. What good is a beep? It sounded completely useless. And yet, let's see where things are at this point. So technology has this nature of becoming more and more and more powerful once the first demonstration has been shown. And indeed, that's what happened. a few years later, with a colleague, Zvika Brakersky, we came up with a second generation of fully homomorphic encryption. So I think of it as going from vacuum tube computing to computing with integrated chips or transistors. And what we did was we used a mathematical framework called lattices. So that's sort of what you see here. It's a two-dimensional grid. That's a lattice, right? Except what we use in cryptography are not two-dimensional lattices. They live in 1,000, or if you ask Jung Hee, 10,000 dimensions, right? But we can make sense of it. It's mathematics. We can make sense of it. And the key thing is that you can use lattices to encrypt data. And how do you encrypt it? You think of your messages, your data, your numbers as being points on the lattice, these green points. You map your numbers that you want to encrypt into these green points, and then you add noise to these points. So that perturbs the point a little bit, and the green point becomes, well, I guess a blue point here becomes a red point. That's the ciphertext. The blue point is a plain text, and the red point is a ciphertext. And what it turns out is that decoding, which is the operation of taking the red point and mapping it back to the blue point where it came from, that's decoding, is believed to be hard. You won't believe me if you look at this picture, because you can do it yourself, but try to do it in 10,000 dimensions. It's sort of what Professor Ryu called the curse of dimensionality now becomes a blessing of dimensionality, and that's really what helps us do this. What it turns out even more magically is that if you have secret information called a trapdoor associated to a lattice, you can actually go back efficiently. So this is really like, if you see a lattice from one point of view, you don't see the structure at all. But what a trapdoor gives you is one particular way to look at a lattice when you see the decoding very clearly, and you can do it. So that trapdoor is the private key of the party who's the only person who can decode the information. The other thing about this form of encryption is that you can actually compute on the encrypted data. You can take two ciphertexts, two of these red points, and add them together. Right? These are numbers, after all. Points are vectors. Vectors are a sequence of numbers. You can add numbers together. And voila, what happens is that you end up adding the underlying plain texts. Right? So this is second grade arithmetic, right? Or I suppose in Korea it's pre-kindergarten, right? So you can do it. Multiplication is a little bit more complicated, and that's what our work was about, to show how to actually multiply encrypted data, which turns out to be a little bit less trivial. But you can do it. And that was a cartoon sketch of our scheme. What happened afterwards in the ensuing decade is that there were several variants of the basic encryption scheme that people came up with, including the CKKS scheme that Professor Chon and his students invented, which actually has this feature that it lets you operate on encrypted real numbers, as opposed to our scheme, which operated on bits or finite field elements. If you think about it, statistics is all about real numbers. It's all about floating point or fixed point numbers. So this is absolutely perfect, sort of marriage made in heaven, if you will, for encrypted statistical computation. So it has been quite influential in the field, really moved the field forward. The other thing that has happened is that people actually took these encryption schemes and they built open source libraries out of it. And at this point, to my count, there are more than 20 open source libraries that implement homomorphic encryption on various platforms with various features and so forth. And there's even a sort of a merger of different libraries that resulted in OpenFHE. You can go to openfhe.org and check it out. And that's really supposedly a more usable version of fully homomorphic encryption. The other thing that happened is a large community grew around this technology, and there's work in programming languages and compilers. So you have to translate programs into programs that operate on encrypted data. So that's programming languages. Hardware that actually speeds up the encrypted computation by a great deal. And standardization. You have an encryption scheme, you have to standardize it. NIST is not going to do it until we demonstrate the applicability of this encryption scheme in a wide scale. So we decided, look, let's bring together folks from the industry, from academia, and the government, and put together standards for homomorphic encryption. And that's what we did starting from a few years ago. There is a homomorphic encryption standardization conference, which I believe next year is going to be in Korea, right, which is super exciting. And this is sort of an annual event at this point with very large attendance. Okay, good. So that's what happened. So what I want to tell you about now is really two things. One, I want to tell you a little bit about applications of homomorphic encryption. In fact, I'll tell you about 3 application scenarios that I see, 3 buckets that you can put your application in. And then I'll tell you a little bit about the challenges that we face. In fact, considerable challenges, but there is hope, really. So scenario 1 is when you have 2 or more parties that all have data. In fact, data of the same type, right? I mean, I have the same type of data as you, as Jung-hee, but we want to put all of it together to learn from the collector. So I call this sort of horizontal data collaboration in a sense. Several examples. Already in 2011, my colleague at MIT, Andrew Lowe, came up with this idea to put together financial information to predict, to learn market health indices, following up from his work on the financial crisis. And again, how do you do this with the financial information being private? Here is something very interesting that happened in Boston. The mayor of Boston had this initiative where he would incentivize companies to ensure pay equity in their workforce. Namely, are women getting paid in parity with men? Are different types of people being treated fairly? If you ensure that, you get incentives. And the point is, once you implement policies that improve pay equity, how do you know that that's happening on an industry-wide scale? You have to do benchmarking, right? Benchmarking on what? On salary data coming from 50 different companies. And of course, you have to do this privately because no company is willing to release fine-grained data on the salaries of their employees. So they did that using a technology very similar to homomorphic encryption a few years ago. A third one that I'll talk about in a little bit more detail is to learn cybersecurity risk metrics from cyber intrusion data, and this is part of ongoing work with colleagues at MIT. So let me tell you a little bit more about this. The context here is that cyber attacks happen all the time. Everybody, if you're worth your name, you get attacked. That happens all the time. But the point is that the firms that do get attacked do not share data relevant to the cyber intrusion. And really, what is the result? Attacks happen, they keep happening all the time, but we don't learn much. This is a quote from Eleanor Roosevelt that I love. It says, you don't live long enough to make all the mistakes yourself. You have to learn from the mistakes of others. And there are good reasons why firms don't just share this data blindly, and that's because of reputational harm, right? If somebody knows that my company gets attacked all the time, that's reputational harm. Legal liability, that's a tangible form of reputational harm. And regulatory scrutiny, you give your competitors an advantage and so forth. So there are good reasons why people don't share this data. But the question is, can you actually do this while ensuring that these companies actually protect their privacy? So we built a platform that does this. And the platform, the idea of the platform itself is very generalizable, but we actually applied it to this one particular problem. We call this SCRAM for Secure Cyber Risk Aggregation and Measurement. You can actually go to this QR code to the website. We have a video that explains what the system does. And roughly speaking, what we do is we brought together a bunch of companies. We asked them to encrypt the relevant data related to cyber intrusion. That includes the incidence of events, the controls they have in place to prevent these events, the losses they incurred, and which controls were implicated for which losses, and so forth. So they encrypted everything and sent it to the SCRAM server, which we operate out of MIT. But because the data is encrypted, we don't learn anything. What we do is we put it together, we do homomorphic computation, and get the parties, send the results, encrypted results back to the parties, and they decrypt it on their end. So this is very similar to the hub and spokes model that Professor Ryu talked about, and I really think that that is a repeatable model. That is something that is applicable across the board for a variety of benchmarking computations. This is just another example. How much time do I have? Okay. All right, so scenario 2 is again 2 parties with data collaborating, but these are different types of data at this point. So now, this is an even bigger challenge, because if you think about the previous setting where all parties had the same type of data, I could have learned something by looking at my own data. I mean, it won't be perfect because I don't have enough data, but I could have done something. Here, this is just impossible. My data is just not informative, because what I'm trying to learn is what happens when I put this together with somebody else's data of a different type. So for example, a bank and a retailer could join their databases to learn correlations between transactions and purchase records, for example. So that I call this sort of secure join and compute or vertical collaboration on data. Yet a third example is when one party has data and the other party has a model, and the sort of data owning party wants to use the model to make a prediction, and of course both parties want to keep data, respectively the model, private. So that's sort of application scenarios. These are 3 sort of broad buckets that you can try to put your favorite use case in. I want to end the talk by telling you a little bit about what I see as the challenges going forward, and challenges mean opportunities. They are exciting because they typically mean that there's more science to do. It's always exciting. So let me sort of start by telling you about a helpful mental model of fully homomorphic encryption. It's going to be a little bit more technical than what Professor Ryu said, but bear with me. So I really think of the world as being the blue world and the red world. The blue world is the world we live in, where numbers are in the clear. We are all statisticians, right? We operate on numbers, we add them, multiply them, we do logistic regression, and so forth. And below is the red world, which is a ciphertext world. And what happens with encryption is that you can take numbers from the blue world, encrypt them, they go into the red world. And what homomorphic encryption does is it gives you ways to operate on objects in the red world, namely ciphertexts. So what you can do is you can add encrypted numbers, you can multiply encrypted numbers, you can do a bunch of things. And what happens without you knowing explicitly what is going on is that these numbers in plain text are getting added and multiplied. Of course, you don't know it because all you see are encrypted numbers. But at the end, once the ciphertext gets to a party who has the key, she can open it up and she can see the corresponding plain text. So this is really what's happening. And the programs that we write in C and Rust and Python in data science languages, they live in the top world. And what we are interested in is to translate those programs into programs that can operate on ciphertexts, i.e. that live in the bottom world. So that really involves reconstructing a version of the entire computing stack that we're familiar with from the 60s and 70s, starting from the bottom, from hardware to the homomorphic instruction set, which says what are the basic operations that are available on encrypted data, to higher level libraries that do linear algebra on encrypted data, to algorithms that use these libraries to perform computations, and finally, looking from the top down, ways to translate programs that you all would write in a language that you love, let's say Rust or C, and compile them down into a form that the homomorphic machine can understand. This is really the top-down stack that we need to build, and there's lots of work underway to work on various, to build various parts of the stack and putting them together. Perhaps the most advanced is our understanding of the homomorphic instruction set. The data types in these encryption systems are vectors, large vectors of numbers, right? Vectors of thousands of entries. And the basic operations on these numbers are addition, multiplication, and a bunch of other things that we'll get to. But really, you should think about, following our discussion from before, you should think about ciphertext as being plain text plus noise. That is a model, while not entirely accurate, is a good model to keep in mind. Yeah, so you have these buckets, these are the slots, different slots of plain text. Yeah, the blue sort of colored things are actually the plain text numbers, and you add some noise on top of it, and you get a ciphertext, right? And what you can do is you can add two sets of two vectors together, you can multiply two vectors together, you can move data between the different slots, and that's I call the slot permutation. And then comes something that really makes our life difficult, which is that when you do operations on the encrypted data, the noise increases. When you do more operations, the noise increases even more, and at some point, the noise becomes so big as to overwhelm the signal, and at that point, the data is useless. The encrypted data is useless. So you have to be very careful to manage the noise, and a very important operation to do that is called bootstrapping, which takes a ciphertext with a large amount of noise and reduces the noise to a manageable level. Once you do that, you can do more operations, and then you can do bootstrapping, and then you can do more operations, and so on and so forth. And that really is a major problem. If you look at the numbers on the right-hand side, you can see that, I'm good, right? Okay. You can see that that is the operation that really takes orders of magnitude more time than everything else. So that comes to challenges. So I'll tell you about three challenges, three things that I see are challenges. Challenge one is efficiency. There's a question of, is fast general purpose FHE possible? Can you encrypt data in a way that people can run any program on the encrypted data? And I really see this as a, and to do that, I really think the way to go is bootstrapping, is to find ways to manage this noise as well as possible. And that really, at this point, seems to need a combination of better algorithms and support from hardware. And a lot of this work is really happening within the last 2 years, and it's very, very exciting. Some of this work is actually happening right here in the Seoul National University. The second challenge is usability. All of us at this point use encryption without actually realizing it. Every time you go check your email, every time you purchase something online, you are using encryption. But the point is that encryption is completely invisible. You're using it without actually realizing that you're using it, and that's where I want homomorphic encryption to be. I want people to write programs without thinking about the fact that it will actually operate on encrypted data, and all of it should be handled in a completely transparent way. That's what I mean by sort of usability or extreme usability. And that really is a challenge, is an ongoing challenge, take many years to sort of get there. But what it needs is it needs good design, it needs good programming environments, and it needs compilers that produce performant homomorphic programs, starting from programs that people write in a high-level language. Challenge 3 is applications. I mean, you heard several applications from Professor Rio's talk. We have constructed other applications. So there is momentum in this field, but I think we are still in search for a killer application. By a killer application, I mean something that will be used by millions of people around the world, ideally in a completely transparent way. We are still searching for it, and there are several sub-challenges associated to actually getting there, one of which is actually getting governments and regulatory agencies to play an active role in enabling homomorphic encryption. I think it's a big piece of the puzzle, and very happy to see all the work happening in Korea. And really, that's all I had to tell you. I really think homomorphic encryption is at least one part of the puzzle that unlocks the promise of collaborative data analytics. And I think the next decade is going to be even more exciting than the past one. So thank you for listening.
네, 최신
We heard about the latest information protection technology of HE and how it can help protect privacy in government statistics. Thank you very much, Professor. And next we have Director Paul Schreier of the OECD Statistics and Data Directorate, whose research area includes national accounts, welfare, non-market activities, and more. The topic is more granular, more timely, the new statistical landscape. Satellite data and new data sources can be linked and used to compile more granular and more timely statistical data, as we will be hearing soon, with real case examples around the world. Director Schreier will also introduce the meaning and role of data stewardship, an international trend in statistical data governance. Please give Director Schreier a welcoming hand.
Good afternoon. It's a great pleasure being here. Thanks so much for this invitation to what is an excellent session. I should say that even though the overall topic for this session was set and organized, we didn't specifically coordinate our presentations, but I must say, looking at the two predecessors, our work is very well coordinated here. What I will do in the few minutes to come is look at the issue of data and the new world of data from a more institutional setting. We've heard from the previous speakers that there are many occasions where you need a third party, a trusted party, where you need government maybe to play a role. So I will dwell on the issue from that perspective. I'll start by setting the scene a little bit and then give you a couple of examples of this new world of data that is more granular, more timely, and typically in a situation where we combine different data sets. So we try to do the type of things that we've just been hearing about to create new evidence for policy and analysis. And then I will go a little deeper into this issue of how do we manage this data ecosystem that is out there? What is the institutions and the setup that we need to get the most out of it? And this will bring me to this issue of data stewardship. So what is the overall picture now? I can be very brief on this, but all of you who have been dealing with data and analysis, certainly most recently through the pandemic, but also financial crisis, and so will have noted that there is an enormous demand and pressure for more timely and more granular data. The pandemic has affected our societies in very differential ways. Women have lived it differently from men, small firms differently from large firms, one region differently from the other. You need good, detailed, and timely data to manage and to understand what is going on. Also, citizens are increasingly expecting to see localized information. They want to recognize their own lives in the data that they get. So all this has evolved recently and has been accelerated through the various events that we are living. Now, just by way of scoping what I mean when I say data in the case at hand, of course, the overall notion of data is very large. You have a little OECD definition here. What I'm specifically referring to is the situation where you take this recorded information and you synthesize it, you aggregate it, you consolidate it, and you document it in line with recognized concepts for purposes of evidence and analysis of the economy, of the society, of the environment. So even though this is pretty broad, it excludes a number of things like medical imaging or so for individuals that we've just hearing about. It's really more from a policy and analytical perspective. It's still a broad field that I'm talking about, but it is pretty much what statistics and statistical offices have been put in place in our countries. The data ecosystem that we observe out there is large and evolving quickly. It's been enabled, of course, by the digital transformation that has offered a myriad of new data sources, but also new tools to exploit and harness the richness of these data sources. Institutionally, what we observe is that the national statistical offices have lost the monopoly of producing data for evidence as I just defined it. A few decades ago, they were the only source of information of this kind by conducting surveys, censuses, and putting them out. Well, you have a lot more these days, a lot more providers. The landscape is fragmented and rich. The issue, and we've already heard this a little bit before as well, is that you do have many sources, but often they are siloed. They don't communicate, or they cannot communicate, and they may be inaccessible for users, for research, for academia who want to tap into these new sources. There is also a phenomenon, because there is so much information and new information out there, the people are looking for trusted information. So they are looking for sources that they can trust in because they think they're giving them facts rather than alternative facts. And of course, there is the tension with privacy, and we've already been hearing a lot about this. I'm mentioning all this because it sets the scene for discussing this need for some governance that may be needed in this data ecosystem, with a view to making the most of it and reducing also the tension between privacy concerns and the promises that the new data sources give us for analysis and, at the end of the day, for policy formulation. So before I say a bit more about the data stewardship issue, I'll just give you a flavor of some of the opportunities in statistical terms that are out there. I'm mainly quoting examples from the OECD. That's just a way of promoting my organization, but of course the scope is much larger, and there are many more examples. I will not go through all of them, but you will see that they all have in common that they combine existing and new sources with a view to getting new insights for our analyses and lives. So a few examples here. One is pretty old-fashioned, if you want. House prices is something that is an important indicator. Unfortunately, the information is not locally available in many countries. You do have aggregate information from official statistics, and you have a lot of detailed privately held information, for example, by notaries on individual transactions. Well, you'd like to combine those and get a consistent set of subnational and national data on house price indexes. And we've done a project like this. The novelty is here that you bring official and private data together, and that you combine it with a little algorithm that makes this whole thing compatible. But this is actually a nice, I was thinking of this example when I heard my predecessors speaking. I mean, this is maybe an area where you can overcome reluctance also of revealing data or sharing data of notaries on individual transaction if you have an encryption system, because that will put this at ease, and I don't have to go through long negotiations to get access to their data sets and have to sign all sorts of legal commitments that can put me in jail if someone uses this data inappropriately. Second example is from the environmental field, and it is a little idea of this enormous potential, of course, that comes with geospatial information. And what we have been doing here is we have been using geospatial information and trained the geospatial information with traditional information from urban atlases, so that the program learns how land use that is available, land use information that is available in these atlases appears in the images and can then paint a picture of the evolving land use basically all over the world and basically in real time. And this is a huge advantage for urban policies, for environmental policies, as you can imagine. And there's no issue, of course, with confidentiality with geospatial data. That's freely available. But it's a good example for, again, for the combination of data sources. And there are other issues that come in here in terms of using this geospatial data. It's very costly to prepare geospatial data, and so there are different roles here that can come in. Tourism trends under COVID, again, this is something where we have been approaching private data holders to be able to get a handle on the impact of the pandemic on the tourism industry. And we've been dealing with TripAdvisor, whom is a website that you probably know, to get an idea about nights spent, arrivals, occupancy rate, again, in a very detailed and timely fashion. This were very interesting results. The problem was, again, actually to get the clearance to publish these, because there were business concerns that came through with the usage of these data or the publication. Another example is, again, about combining geospatial information with traditional census data. You are able to detect air pollution, or in particular the particulate matter that is in the air from space. And if you combine that information with the population density figures that you get from our established censuses, you can compute the exposure of the population to air pollution in a very fine way, almost by square kilometer, for the globe as a whole, as long as you have the basic census and population data there. And that creates very interesting analytical tools. And again, it is about combining sources of very different nature in an efficient way to go further in the exploitation of these possibilities. Last example doesn't come from the OECD, but which I found very interesting also in terms of the institutional setup in the United Kingdom, but also in other countries. I just quote the UK here. The issue during the pandemic was to get a good idea of the infection rate of the population. And of course, if you only monitor the testing results of those people, of those persons who go and take a test, you are never certain that you have a representative image of what is happening in the population at large. Well, what happened in this case here was that the UK Office for National Statistics used its census, its sampling frame, to define a representative sample of the population, England and Wales, and these people were all tested. And that gave rise, on a weekly basis almost, to a very accurate picture of the infection rates in the UK during the pandemic. It goes to show that, again, we are in a situation where a traditional tool, a sampling frame that the ONS uses for its surveys, is being combined with completely different information, medical information in the case at hand. So from these examples, you can see the potential, which of course goes way beyond what I've just been describing, comes the issue, well, how do we make the most of these situations? How do we overcome the issues that are involved in using such disparate sources of the ecosystem? We need, and that's in a way the core of the point that I'm making, we need a data stewardship. What do I mean when I say data stewardship? Let me first briefly define data governance. Data governance is, in our definition, the overall decision-making, the authority for data-related matters in society. So we're talking about very basic policies, privacy laws, statistical laws that exist in our societies to govern the data. Data stewardship is somewhat more narrowly defined. It is about implementing these policies, setting standards and principles of data governance in the area of data for evidence that I just defined before. And you can see already in a number of countries that the role of data stewardship is something that is picked up by institutions. And typically, of course, it is the National Statistical Office that, whose role is progressively transformed from a simple data producer to a data steward in the country. You have data stewardship within companies as well. That's sort of the microeconomic correspondence to it. Now, looking at these data stewardship roles as they occur in countries, we observe that there is no single model, of course, but it typically involves a number of things that these data stewards do. The first one is they are actively coordinating and standard setting actors among the producers of official statistics. Now, in virtually every country, you have not only the National Statistical Office, you do have other producers of official statistics, like the central bank, like statistical outfits of ministries who are part of the national statistical system. Well, the data steward's first role is to set standard guidelines and work towards interoperability among those who actually already officially produce statistics for the country. Then you can cast the net a bit wider and look at administrative data that is held more generally, but not necessarily with a view to producing statistics. So, you know, the Environment Ministry has data for its own purposes, the Health Ministry, so on. All these are rich sources that deserve to be exploited. And again, the data steward's role would be to facilitate the usage of these data for evidence, for analysis, for policy. This is also where issues like encryption would come in, because this is exactly the kind of situation that you face, that the Health Ministry doesn't want to share its data with the Environment Ministry for good reasons, probably, and the new tools that we've just been hearing about can help in those situations. But someone needs to organize this. Someone needs to say, let's sit down and put these things together, and that would be the role of the data steward. In the broadest sense, a data steward has also a function vis-a-vis the private sector, vis-a-vis private data holders, like all sorts of companies, for example, through a promotion of standards, terminology, classifications. Those are pretty boring, but very, very important things, that things are labeled similarly and conceived also with a view to using information for statistics at the end of the day. I mentioned this last point here is the once-only principle. That is a demand that we have increasingly from society itself, where people or businesses in particular say, we are more and more reluctant to respond to surveys and to provide information about ourselves more than once to different parts of the administration. So it is a challenge for our governments also to organize things such that when information is collected by one part of the administration, that it then can be shared with other parts of the government. And again, it's about data sharing, it's about organizing this ecosystem. Thank you. What are the ingredients needed to get to this point? The first is you need a strong legal and ethical basis. You need statistics laws, you need implementation, of course data protection laws, you need ethical standards, you need an ongoing dialogue with society's stakeholders to get to a position where there is trust also in this institution. It's sort of obtaining a social license to go forward in this space. This is a bit sort of qualitative material, but trust in institution is extremely important in this setting, so that the data steward has the confidence of society to do what it is asked to do. We need common standards and interoperability. I already mentioned the issue of classifications. Use data between different parts of the administration. Well, they're classified very differently. You want some metadata standards, quality frameworks that are more broadly applicable than just among statistical producers. And of course, you want the data to be able to speak to each other, be it directly or openly or in encrypted form. So those are all tasks that need to be put in place. I'll skip the example here, just mention maybe Switzerland, where a lot of work has already been done, and moving in the direction of having the Swiss Federal Statistical Office as a data steward for the country. That includes the interoperability of the sources among the different parts of the administration, but it also a new role for the Statistical Office in the sense of offering access services to academia and researchers in terms of the microdata that sits in different parts of the administration. So they advise, they consult, they actually help, and they ensure, of course, confidentiality by helping researchers doing this. So this is a different role that comes along with these developments. Quality standards, so trust again, is created by making sure that that data that is being produced from different sources is compatible with international quality standards. I'm just reminding you here that quality is not only about accuracy of data. Data quality is also about relevance. I mean, this is what I'm producing. Is it useful? It is about accessibility. Do I find it easily? It is about documentation. Is it is the metadata well developed? And so there are a number of quality criteria that all need to be put in place to acquire this trust that is needed for that role to go ahead. Finally, co-investment. Co-investment is something that is a matter of efficiency in many ways. Different institutions all face similar issues, and yet very often each of them pursues their own way of going forward in exploiting new sources, in forming new platforms, in conducting research. At the international level, we are trying to promote co-investment in data management, in data platforms. I'll give you, I'll just stick with two examples. One that is led by ourselves, by the OECD, it's called the Statistical Information System Collaboration Community. You see the set of institutions that basically co-invest, so they all put money into developing a data management platform that is then deployed individually and used in each of these institutions with sort of customized versions as they are deployed, but the core of the matter is developed jointly. It's a community, it's open source, it's compatible with international data exchange standards. And of course, it is much easier to do this collectively and much cheaper than if each of these institutions were building their own data management system. Other example is, again, about tapping into new data sources. The International Monetary Fund has launched, and we joined, as well as the World Bank and the Inter-American Development Bank, what is called the Development Data Partnership. The idea is that collectively the international organizations approach big digital players. You have the names here on the slide, with a view to being able to use their data for analytical purposes. And the advantage, again, is that there's only one protocol that is established, say with Google, to use their data, and the legal issues are resolved collectively. And it's all about co-investment and cooperation. And the idea is, of course, that this can be brought to a different level, not just between three international organizations and those players, but that this takes more space and also helps national statistical offices who may very well be interested and are interested in data from these organizations. Think of LinkedIn for labor market statistics, and I mean, each of them has something to bring to the richness of the data set nationally. So co-investment or collaboration is important. And again, a data steward needs to be there to organize the space and to have the mandate to bring players to the table here. So to conclude, we are in a whole new world of data for evidence. There's an ecosystem out there that creates enormous possibilities to generate new evidence for policy. But the evidence must be coming from a trusted source. It must be granular and timely enough to respond to demands of citizens and policymakers. I think that the avenue of data stewardship is something that needs to be pursued institutionally, and I do think that national statistical offices do have an important role to play in transforming themselves gradually into data stewards in our countries to make these things happen. So thank you very much for your attention.
네, 통계
Thank you very much. We heard about new cases in other parts of the world on statistical data usage and governance and the way forward on making more use of statistical data. Thank you very much for the presentation. And we are now ready for the panel discussion. We've heard in-depth presentations on the current and future use of statistical data through innovation. Now it's time to listen to the conversation of our experts as they share their views. Professor Keun-Kwan Ryu of SNU will moderate this panel, joined by Professor Jung-hee Chun of SNU and the presenters, Professor Vinod Vaikuntanathan of MIT, and Director Paul Schreier of the Statistics and Data Directorate of the OECD. Please come forward to the stage. And please give a welcoming hand to all our panels.
Okay, I'll start by saying thank you for audiences here and also the participants through online. Some of the talks are little bit difficult for general people, but still you participate in this session throughout, so I very much appreciate it. I'll first pass my mic to Professor Chun Jung-hee. As I said, he is the Mr. C in the so-called CKKS homomorphic encryption scheme, which is very useful, as Professor Vaikuntanada mentioned, for the purpose of computing statistics using real numbers, because we most often live with real numbers. So, Professor Chun.
Thank you for introductions. I really enjoyed all the talks. Let me briefly summarize the role of cryptography for computing. So the purpose of cryptography is to protect all the components of computing. So the computer's job can consist of three things, like storage, first storage, and then transmission or communications, and then computing. So traditionally, storage is protected by cryptography. And then from the 1970s, also communication can be protected by cryptography, so-called using public encryption. But the computation is outside the cryptography. We cannot protect computation with cryptography, so it's protected using some other tools, like some security tools, using hardware, software, but they are not perfect. Now, with homomorphic encryption, we can protect computation also. So, using HE, we can protect all of three components of computers, like storage, communications, and then computations. So without secret key, we can do all the things any computer can perform all the functionalities without unencrypted data, without secret key. Now, yeah, it's perfect. So then the problem is when we can use this homomorphic encryption in practice. Also, we need three components to be used in practice. The first one is regulation, and second one is functionality and speed, and third one is usability, I think. So for the regulations, now it's time for ISO standard. Next month, we'll have a vote for a working draft of fully homomorphic encryption in ISO. So yeah, in 2024, it will be completed. So FHE standard in ISO. And then we have several regulations in data laws, so including GDPR and then Korea 3 data laws. So now we are starting to use, we are making some regulations about those new tools. I think we can do, as we understand more, and then we can make some better locations for homomorphic encryption in GDPR or data laws and CCPA. And then for the functionality and speed, what we can say is, as Vinod told, so homomorphic encryption was very slow, but nowadays it's I can say that several thousand times slower. So it's still very slow, but we are developing hardwares, some homomorphic encryption accelerators. We are expecting 10x times slower with one accelerator chips in 2024. It's ongoing with DARPA project and with some many by some researchers and hardware companies. What does it mean by 10x? If we use these accelerator chips, all the homomorphic encryption, all the homomorphic computation can be done only 10x, 10 times slower overhead. 10 times is a bit large, but it's like 5 years computing 5 years ago. It was slower, like 10 times slower. So we can enjoy homomorphic computation with this speed, but with perfect secrecy. So, and then the last piece is like the applications and then usability. So I think one of the most interesting application is homomorphic statistics. Cross borders, all the nations, all the countries have their own data, but worldwide, we need to get some statistics over the countries. But it's very hard to share for the countries to share their data, their private data. So using homomorphic encryption, we can perform encrypted statistics, that we can get some statistics on encrypted data without worrying about the privacy or any risk. So I really appreciate the Statistics Korea and then Commissioner Han Hun and then former Commissioner Ryu Geun-kwan for this effort. I think we can read, the Korea can read these important applications, and then so that all the world can enjoy these very interesting and then very useful tools. Yeah, thank you.
Thank you for very promising and exciting prospect for the future of homomorphic encryption. Personally, I think that I'm very honored to be on the same campus with Professor Chen. He mentioned 10x. 10x means that if you use homomorphic encryption, are you willing to wait 10 seconds to see the outcome rather than 1 second to protect your privacy? Yes, I will be willing to wait. So that's my expectation for what he mentioned regarding 10x. Now I will ask Professor Vaikunthanathan. In the tea time, I jokingly said that his last name is encrypted. His last name is in fact very simple, but through encryption, rather long. Vaikunthanathan. Please understand my joke. He was mentioning killer application. I personally think that government statistics is strong candidate for killer application. Why? Because government statistics doesn't need fancy neural network models with a lot of hidden layers. And the government statistics, if it's available in 1 hour, 1 day, even in 1 month, not such a huge problem. Unlike online recommendation system. In that case, business people need speed because otherwise customers don't wait 10 seconds. They want answer immediately. But government statistics is not like that. Therefore, I personally believe that government statistics is one strong candidate for killer application using your term. So how you think about that?
Is this okay? Yeah, so that's a very interesting perspective on where things are going. So the way I think about it, a killer application should have a few characteristics. For homomorphic encryption, should have a few characteristics. The first one is that it has to demonstrate value. In the sense, homomorphic encryption does something that you couldn't have done otherwise. because of privacy concerns or regulations or whatever. So that's the first step. You have to demonstrate value.
이것이 첫 번째 단계입니다. 가치를 제공한다라는 것을 증명해야 하는데 류 교수님께서 말씀하셨지만 한국통계청에서 하고 있는 일이 이제 서로 다른 성격의 두 출처에서 나오는 서로 다른 성격의 데이터, 서로 간에 공유할 의지가 없는 그러한 데이터 세트를 교환할 수 있도록 합니다. 공동의 데이터베이스를 구축을 해주고 거기다가 이제 연산을 하면 됩니다. 그래서 안전한 공동의 어떤 연산을 하도록 하는 것입니다. 그러니까 각각의 기관이 따로따로 이것을 할 수는 없습니다. 그래서 같이 데이터를 합쳐서 같이 이제 분석을 하는 것이고 이것이 첫 번째이고 두 번째 특성은 연산 중에 좀 단순 연산을 좀 파악해야 합니다. 그러니까 너무 복잡한
Like Professor Ryu said, and they are all over the place. You don't need complicated neural networks for 90% of your life. The third thing is non-real-time nature of the computations. In the sense, you're trying to learn something that you're willing to wait for hours a day, and things are going from hours to minutes to seconds in homomorphic encryption these days. So really, I would say, if you are willing to wait for the results about the same time as you would go get coffee, then that should be perfectly acceptable for you, 10x or 100x or whatever, it doesn't really matter. And the fourth and final thing is that homomorphic computations become a lot easier when data is presented in a nice format, in a clean format. I.e., the metadata is clear. What is being sort of encrypted is clear. The format is clear. Is it a real number? What is the precision? And so forth are clear. When that happens, it becomes so much easier to do homomorphic computations compared to unstructured, unclean data. So I think there are many applications, including the ones Professor Ryu talked about, which combine all four characteristics, and that's what makes it very promising.
Yes, Paul, please.
We know those were really, really interesting conditions for good applications, and it made me think of a situation that was just happening in my home country, actually, in Austria, where the energy crisis has driven current prices for electricity through the roof. So the government wanted to provide some support for energy pricing. The way this is done was that a base consumption was granted to households at a subsidized rate, and everything else was paid by the market price. The big criticism of the measure was that that applied to all sorts of households, irrespective of their income or wealth. So there was no social targeting, means the measure is quite expensive. The reason why this couldn't be done was because it was impossible to combine the information about electricity consumption that was held by the electricity companies with the information on household income that is held by the fiscal authorities. And obviously the fiscal authority said, we'll never hand over our information to the electricity companies who actually wouldn't even want it. And vice versa, the electricity company says, there's no way we transmit this data to the fiscal. Had there been a system of encryption, as you described it, that could have happened very quickly. And I mean, if you say the waiting time is, we're talking about hours or days, I mean, that would be perfectly acceptable and would have saved a lot of money to the Austrian governments and produced a measure that is more targeted socially than the current outcome.
Yes, thank you. The father of economics, Adam Smith, mentioned that the price mechanism is kind of invisible hands. Now, homomorphic encryption, by making data invisible, paradoxically, I personally think that it will make the world more transparent. By making data less transparent, it contributes to transparency of society, so that's a wonderful thing. Mr. Paul Schreier, he is a chief statistician of OECD, so he is a leading OECD statistics standard and coordination among international organizations. In your presentation, you mentioned differential impacts of a certain policy, which requires granular data, microdata, less aggregate data. Obviously, less aggregation expose privacy issue. Therefore, I think the demand for privacy preserving tools is increasing over time, even at world level, including OECD. So how do you think about that aspect?
I think your analysis is absolutely correct. And there is this tension between the desire to exploit the individual sources, the new sources, for policy, for good policy, but at the same time, society is increasingly aware of the privacy issue and the need to protect it. And yeah, I see really many possibilities to ease that tension that comes through these technical developments that I see here. I mean, what is interesting is that almost up to now, I mean, we were always insisting on the fact that you need the institutional and the legal environment to make things happen. That technology wasn't actually very often the most important thing. I mean, think of accessing individual confidential microdata in countries. Technically, that's not a big deal. The big deal is to make it in a way that it is compatible with the institutions and the laws. And so that used to be, or is very much the stumbling stone. What is interesting here is that the technology itself makes it easier to implement the laws, implement the restriction, goes forward. So it's not just, okay, something on top of it. It actually is a dynamic process that facilitates our work in that direction. So I think this is a really exciting field, and I'm very pleased to observe that countries like Korea are so actively engaging in that process.
Thank you. Now maybe I will ask some of the audiences to raise a question if you have. You can ask in English or in Korean, either way. So any question from the floor? Okay, then we'll continue discussion, and then if any time if you have questions, then please raise your hand.
I have a question actually to Paul. So if we do the statistics on encrypted data over the countries, does it commit the or GDPR or OECD rules, or it's completely safe? So do you have any answers for this one?
I don't have a very clear answer, but the application that you mentioned is a sort of a killer application. I'll tell you why. A big problem or not a big problem, a fact is that national statistical offices obviously only collect information on national or residential actors. Well, why does this matter? It matters when it comes to multinational companies. What Statistics France measures in France are the subsidiaries of Apple or Microsoft that operate in France. And what is measured in the UK or in Ireland are the subsidiaries that are operating there. No single office has a complete picture of the activities of a multinational enterprise. Yet that would be extremely interesting for many reasons, economic analysis and taxation and the move of assets. And the problem is, of course, that it is legally very difficult, if not impossible, to exchange this microdata on individual subsidiaries of companies between countries. Even if it's statistical offices who have all the tools to do so, that is very difficult to put in place. There are some efforts now within the European Union with legislation slowly evolving, but it's a very, very long process. So if there was a very safe technical solution for this, I mean, that could change, that could be a game changer going forward. So I think that's why I think your example is actually very relevant.
Time is pretty much up, I think, so I think I had to wrap up this session. I very much appreciate Professor Vaikunthanadan and Mr. Paul Schreier coming all the way to Seoul for this important session, and I also very much appreciate Professor Chun Jung-hee to join this panel discussion. Most of all, I appreciate audiences offline and also many audiences participating in this conference online. Thank you very much, and I think this session will contribute a lot, hopefully, toward transparency and the cooperation of different data owners in Korea as well as all over the world. Thank you.
Thank you very much. A round of applause to our speakers, please, for seeking the future use of statistical data. We have reached the end of the session already. I would like to thank all distinguished guests here on site and all online participants for staying with us throughout the sessions. Thank you very much, and this ends the session. Thank you.